All right, so last time revolved around calculating pH. So let's just remember pH is the negative log of the concentration of hydronium ions. Oh, sorry. Trying to do it again. All right, my bad. The groups you can work by yourself if you want. They're maximum of 5, so from 1 to 5 people. All right, so pH, negative log of the concentration of hydronium ions. All right, and what we should know from our algebra class, but of course if we're not algebra experts, that's cool, we can go through it explicitly, is how to go the opposite direction. All right, what if I want concentration of hydronium ions? All right, the inverse is taking 10 to the negative pH. Okay, that's the inverse of a logarithm. So if I wanted to go the opposite direction, I would take 10 to the negative of whatever my pH was. All right. Way less popular, but nonetheless a sort of similar concept is now POH. And this is just the negative log of the concentration of hydroxide ions. Right? Also, if I wanted to go the opposite direction, again, that inverse is 10 to the negative. In this case, POH. All right, and then we talked about these acid dissociation constants, these Ka values. Sometimes you'll see them listed as pKa's. What do we think a pKa is? What's that P been doing for us? Negative log, right? So in this case, a pKa is just the negative log of that Ka value. All right, so again, P means take the negative log of something. All right, we also had this very important autoionization relationship. Okay, and then you can derive this next formula by just taking the negative log of both sides of this equation, or you can just trust me. But if we take this autoionization relationship and we take the negative log of both sides, we would simplify that to is that pH plus our POH equals 14. These are both the same thing. But this is in log space. All right, I've taken the negative log of both sides. There may be situations where it's more convenient to use one or the other, but you could always use either one and get to the same answer. All right, sometimes it'll be more steps or something like that. Like again, one might be more convenient, but either one would work because again, they're both sort of saying the exact same thing, right? All I did was take this autoionization relationship and take the negative log of both sides, do some algebra, and that simplifies to that. All right, and then where we ended last time was calculating the pH of a weak acid solution. So let's go through an example here to remind ourselves. What is the pH of 0.75 molar solution of butanoic acid? All right, butanoic acid, is that a strong acid? No, it's not on our strong acid list, right? So what are we going to need in order to be able to solve this problem? Ice table, and specifically we're going to need to know the value of that equilibrium constant. Okay? So one part of our constants page for this particular chapter are the formulas that we just looked at, but also importantly this table here. This is our table of Ka values for all of our weak acids. Right? So if I need to figure out the pH, I'm going to look on my Ka table for butanoic acid. That would be 1.5 times 10 to the negative 5. That's the value. That's that Ka value that I'm going to need. Okay, so we can just make a note. Ka 1.5 times 10 to the negative 5. All right. And in order to solve this, you're going to give me the equilibrium expression. And then how do we fill in that equilibrium expression? We use our ice table. All right, so set those two up. I guess even before that, I need my balanced chemical equation. All right, so I need my balanced chemical equation. What am I going to be reacting my butanoic acid in if I'm talking about this, taking the pH of this solution? Water, right? So we always have the same sort of basic structure of our chemical equations, and that's our acid plus water gives us hydronium ions, and our conjugate base, which is in this case, I'm just going to take a hydrogen away, so HC4H7O2. And what am I going to have to do to finish off this formula? I decreased my hydrogens by 1. What else do I have to do? The charge, right? So you take away a hydrogen, but you also have to tick down that charge by 1 as well. Oh, sorry. Jeez, it's early. Products over reactants. Jeez Louise. Making sure y'all are paying attention. Hydronium ions are, of course, a product. They go on top. All right, so I got my Ka expression, and then in order to fill in that, replace these variables here, I need to build my ice table. Now I have the value of these concentrations at equilibrium. So I'm going to take that information and plug it back into this equation here. So I would get that my Ka equals x times x, or x squared, over 0.75 minus x. Okay? Now, because x is going to be so teeny tiny, what assumption can I make about this that's going to save, make my algebra that much easier? Yeah, right? What can I drop? I can drop this minus x from my denominator here. You could solve it with that in there. It's totally doable. You would have to use the quadratic equation, all right? But you can just make your life a little bit easier algebra-wise by dropping that x. So this is about the same thing as x squared over 0.75. All right, and then we looked up that Ka value, right? So I know that this is going to be equal to 1.5 times 10 to the negative 5. Now I just got to do some algebra, rearranging this equation to solve for x. All right, and so what I get is that x equals 0.003354, blah, blah, blah. All right, so I'm done? No, why am I not done yet? I got x. What is x, though? X is the concentration of hydronium ions. So if I had asked you for the concentration of hydronium ions, we'd be done. But I didn't ask you for the concentration of hydronium ions. I asked for pH. So we're going to have to make sure to take the negative log of that value, right? Again, it's sort of easy once you get to that step. You're doing a bunch of algebra. You kind of forget what it is that you're solving for. Make sure to check back at your ice table, right? X is just the concentration of hydronium ions. So in order to get the pH, I'm going to have to take the negative log of x. And for these, we're not going to worry about sig figs, so I'm just going to tell you 2 decimal places. All right, so how do we solve these weak acid problems? Again, we're going to start with our balanced chemical equation. From there, we can build our equilibrium expression. Then we got our ice table. That's what helps us fill in our equilibrium expression. Then we're going to combine that expression with our ice table and solve. All right, so we're going to practice this sort of similar structure when we talk about weak bases, because that's going to be our topic that we're introducing today, bases. So when we have a base in solution, so for example, now we're going to be reacting a base with water. Everybody take a second. Remember, we learned how to do the formulas for our conjugate acids given a base. So everybody take a second and draw me the product of these two reactions here. Here, water is playing the role of the acid, and in this case, NH3 is my base. So predict the products of this reaction. All right, what would my conjugate acid be? I'm going to take my base and do what? Am I going to increase hydrogens or decrease hydrogens? Remember, bases accept protons, so I'm going to increase the number of hydrogens. So this becomes NH4. And then what happens to the charge? Does it go up or down? Charge goes up by 1. For my conjugate base, I'm going to take my acid, which is in this case water. I'm going to decrease the number of hydrogens by 1 and decrease the charge by 1. You can also write this OH minus 1, either one, and they're perfectly equivalent. All right, and this is, of course, what we call what? Does anybody remember the name of OH minus? Hydroxide. So we'll see that in a basic solution, our product is always hydroxide ions, right? For an acid, it was the hydronium ions. For bases, we get a hydroxide ion. All right, for bases, we also have this concept of a strong base. Whoops. Right, and just like for strong acids, our strong bases completely dissociate, right? That reaction goes 100% to the product side. So just like with our strong acids, kind of best case scenario if you have a strong base in terms of calculations, because you get to say that the concentration of your strong base is just equal to the concentration of hydroxide ions. All right, and for our strong bases, they're going to be actually a little bit easier to identify than our strong acids because it's just going to be any ionic compound that has an OH in there. All right, so for example, sodium hydroxide, potassium hydroxide, cesium hydroxide, strontium hydroxide, right? Any sort of ionic compound that has those hydroxide ions. Should be good and include the word soluble, but I'm not going to like randomly throw you an example where it's not that case. So. All right, so again, what type of problem can we do with this information? I could ask you something like, what is the pH of a 0.075 molar solution of sodium hydroxide? All right, so I know my concentration of NaOH is this 0.075. And since this is a strong base, I know that that concentration is just equal to the concentration of hydroxide. All right, but since we're talking about bases, if I want the pH, I got to do one extra step, right? I got one more consideration to make. And if we look back at those formulas that we were talking about at the beginning, I'm going to have to use this auto-ionization relationship. That tells me if I know the concentration of OH, I can always find the concentration of hydronium, right? Because again, those products have to be equal to 10 to the negative 14. Right, so given that I have this OH concentration, I can use this relationship here. I'm going to rearrange it to solve for hydronium ions, solve for this thing here. So I'm going to divide both sides by that hydroxide ion concentration. Right, so that's 10 to the negative 14 over 0.075. .3 continued times 10 to the negative 13. So then my pH is just the negative log of that value. How many decimal points should my pH have? 2. All right, remember sig figs in concentration will be decimal places in log space. All right, so since I have my strong base, I know the concentration is equal to the concentration of hydroxide ions, right? But if I want the pH of this solution, I'm going to have to use this auto-ionization relationship in order to figure out concentration of hydronium. Then I can take the negative log of that to get my pH. The other way that you could have solved this, which is perfectly equivalent, is I could have first gotten my pOH by taking the negative log of that 0.075. I would get 1.12. All All right, and then use the fact that pH plus pOH equals 14. So that pH has to be that same 12.88 value. All right, either one of these methods would be equivalent, right? Again, you got to use that autoionization relationship, whether you use it in its normal form, like up here in this first example, or in this log form, it doesn't matter. Again, the approaches are equivalent, all right, whichever one you find to be more convenient. All right, but now, similar to what we saw before with weak acids, now we have weak bases. They do not fully dissociate. All right, so what do we think we're going to need to do to solve these? Ice table, right? So this is again going to be like how we did weak acids. We're going to start with our balanced chemical equation, build our equilibrium expression, and then we got to do an ice table to fill it in. Okay? So if we go back to this equation here, is ammonia, NH3, is that a strong base?
No.
How do I know it's not a strong base? Because it's not got a hydroxide in it, right? Truth be told, if you go on to organic chemistry, you'll learn about a few other strong bases that exist. We're going to stick to this simple rule of it has a hydroxide in it. All right, those are also by far the most common ones. There are strong bases. They're just more expensive, fancier. All right, so we're going to stick with that simple rule here. All right, so then I have my balanced chemical equation. Okay. So again, step one, balanced chemical equation. Step two, build me that equilibrium expression. All right, I'll be good and put in my states up here. All right, I got my products, concentration of products over my reactants. I'm not going to include water though because it's a pure liquid. Okay, and so for bases, we call it Kb. And where do we think we can get the value of Kb for our bases? Right, so from our constants page. So if we go back to that same posted constants page, if we look down at the bottom, now all of a sudden we see a bunch of Kb's listed for different bases. So I'm going to find my NH3, my ammonia, and I see that the Kb value is 1.76 times 10 to the negative 5. All right, so now build me my iced. Oh, I guess we need an initial concentration. So let's say, what is the pH of a 1.0 molar solution of ammonia? So now I'm going to plug my ice table into my KB expression and solve. All right, and just like before, I can make this assumption that x is going to be really tiny. So I'm going to just drop that minus x from my denominator. So this is going to be the same thing as x squared over 1.0, and that equals my 1.76 times 10 to the negative 5. All right, so I get that my x is 0.004195. All right, am I done? No. So this is where we got to be really careful here. Everybody's like, oh, I got my x. Let me take the negative log. We could do that. So let's say that I take the negative log of x, and I get 2.38. We're just going to do 2 decimal places. Am I done? Is that my answer? No, because importantly, what did I just calculate here? The pOH, right? Remember, unlike when we were doing our acid problems, when we solved for x, x was the value of the hydronium ion concentration. But now that we're talking about bases, x is the value of my hydroxide ion concentration, right? So this would not be pH, but pOH, right? I took the negative log of the hydroxide ion concentration. But that's cool. I can get to pH really easily from pOH, right? I just got to remember that pH plus pOH equals 14. So my pH would equal 14 minus that pOH, or 11.62. All right, but again, just remember, it's very easy to kind of get lost in your ice table, turning numbers into other numbers. Take a step back and remember what it is that you just solved for, right? In the cases of bases, that x value is the concentration of hydroxide ions. So if I want the pH of that solution, voice crack, if I want the pH of that solution, I'm going to have to use my auto-ionization relationship, pH plus pOH equals 14. Cool? All right, so now last one is we're going to do the pH of a 0.653 molar solution of fluoride ions. Okay, so I'm going to do my balanced chemical equation. With water. All right, the fluoride ions are going to be playing the role of the base. So that means that water is my acid. All right, or is playing the role of an acid here. So everybody take a second to predict the products of this reaction. All right, so does my base increase in hydrogens or decrease in hydrogens? Increase. So this is going to be HF, and then what happens to the charge? Goes up by 1 as well, so in this case it's going to be neutral. I get these hydroxide ions. All right, what's the next step? KB, exactly, my equilibrium expression, right? So everybody take a minute to build my equilibrium expression, or the equilibrium expression. All right, so I got my KB expression. Now, if I go to my table here, and I'm trying to look up the KB value for fluoride, I'm not going to be able to find it in this section right here. Okay, if you look through there, you won't find fluoride listed. So how do I go about getting my KB value? All right, so there's this important relationship that we haven't talked about. If I have a base okay, if I have a strong base, like as is the case with my hydroxide ions, take a second and draw me my conjugate acid real quick. What's the conjugate acid of hydroxide? Water. Right? Increase number of hydrogens, increase my charge. The conjugate acid of a strong base is just neutral. Right? It doesn't affect the pH at all. However, if I have a weak base, like for example my fluoride ions, its conjugate acid is a weak acid. All right, and this is going to be very important when we talk about buffer solutions next chapter. Likewise, if I have an acid and I'm predicting conjugate bases, if I take a strong acid like HCl, its conjugate base is also neutral. But if I take a weak acid, the conjugate base of a weak acid is a weak base.
The conjugate parts, while they're still weak, they're still stronger than the original weak.
Yeah, so we have like strong on one end, we have neutral, meaning it doesn't affect the pH at all, and then we have weak, which will affect the pH. right? So weak doesn't mean negligible. You don't have to consider it at all, if that was your question. Okay, so what I'm going to find is I don't see fluoride listed on my table here. But if I look under my acids, I will find HF, right? The Ka value. And there's this very simple relationship between Ka and Kb. Ka times Kb is equal to that same 10 to the negative 14 value. Right, so to find the Kb of the fluoride ion, I need to look up the Ka of HF and then use that relationship up there. That's how I'm going to get my Kb. All right, so hydrofluoric acid has a Ka of 6.8 times 10 to the negative 4. So then my Kb is 10 to the negative 14 divided by that Ka value. Ah. All right, and now that I got my Kb value, I can just go ahead and solve this problem just like we did the last one. All right, so for the interest of time here, let me just give you sort of the final answer to sort of note down so that you guys can have that to look at when you're doing your problem. All right, so you'll again build the ice table. Combine steps 2 and 3 and solve. Again, you got to be careful because the X value that you're going to get at the end is actually the PO, or is the hydroxide ion concentration. So you'll use that auto ionization relationship in order to get the POH here. Why does that seem so low?
Subtle noise, like a squeak, is a subtle noise. You're dying, bro. It's a squeaking little thing. What pH did you get?
You know how you get the X value? How do you put this into a calculator?
Well, so you got to move this value over. So you would do 1 times that, right, to move the 1 out from underneath. And then you have x squared equals that times 1. How can you get x?
Wait, so it'd be like 1.76.
1.76 times 10 to the negative 5.
That
times whatever's on the denominator here, which is just 1. Okay? So now you have x squared equals that value. How do you solve for x?
Oh, and then you square it, right?
Square root. Yep.
When I divided for the KB, I got 1.7.
So you got to be careful because you're dividing your number in scientific notation. So what it did is divided by 6.8 and then multiplied the whole thing by the 10 to the whatever.
So put it in parentheses?
Put it in parentheses when
Both
you're
or just
dividing.
the last part?
Just the thing you're dividing by.
Okay.
Right? That's what keeps it on the denominator.
For this question on the weak acids, how